Welcome to the debate. Our focus today is on the seismic shift that's underway in wireless connectivity, the transition from 5G to 6G, which the industry is projecting for commercial arrival around 2030. And this isn't just a number change. The performance targets, we're talking terabit speeds, sub-microsecond latency. They suggest an entirely new class of digital experience.
Indeed, the raw quantitative targets are staggering. And they really force us to confront the nature of technological progress. The source material lays out this dramatic progression, which brings us to our central question.
Absolutely. The core disagreement we're tackling, and this is pulled from industry roadmaps and research, is this. Does the transition from 5G advanced to 6G represent a fundamental, revolutionary paradigm shift? Something driven by intentionally disruptive new technologies? Or is it better characterized as an evolutionary scaling of concepts that were already in 5G advanced, just required to overcome known physical limits? Look, my position is that 6G is a true forced revolution, and it's necessitated by 5G's fundamental architectural and physical ceilings.
I just find that interpretation a little too black and white. While the leap in performance is massive, I'm going to argue that 6G is an aggressive yet necessary evolution. Every single major pillar of the 6G roadmap is deeply anchored in the foundational prep work, what the source material itself calls the crucial evolutionary bridge, laid out in 5G Advanced, specifically in 3GPP releases 18 and 19.
My position is really rooted in physics and architecture. 5G fundamentally hit an insurmountable floor in three critical areas: latency, available spectrum, and topology. We can't just tweak 5G's established standards to get to the 6G targets. The shift requires introducing technologies that, they rewrite the rules of wireless communication. Just consider two key elements: terahertz or THZ communication and integrated sensing and communication, ISAC. 5G's millimeter wave architecture, it just fails to penetrate buildings effectively and is severely limited by spectrum congestion. So to leap to 1 terabit per second and achieve true immersive applications like, say, holographic telepresence, 6G has to exploit the THD band. This demands entirely new materials, new beamforming techniques, and architectural approaches that 5G just cannot support. And when you couple that with ISAC, which transforms the radio from a mere connector into an intelligent sensor, 6G fundamentally redefines the network's function. It moves beyond communication into environmental awareness. That is a revolutionary architectural break.
Okay, I respect the focus on the physical necessity, but I frame that necessity as the natural, forced conclusion of an evolutionary path. The source material clearly outlines that the research, the standardization, and even the initial physical explorations for these so-called revolutionary pillars were formalized within the 5G advanced timeline. For example, 5GA already introduced non-terrestrial networks, NTNs, in Release 18. That aims for 100% global coverage, which is a core 6G promise. And crucially, the intelligence aspect, the supposed AI native core, that evolved directly from 5G's network data analytics function, the NWDF, that was the reactive AI engine introduced in 5G. 6G's autonomy is just the maturation of this intelligence, and it was required because the massive complexity introduced by 5G's virtualization made fully autonomous operation unavoidable.
We're not building a new city here. We're using new construction techniques to finish the hyperscale vision that 5G started but couldn't quite complete because of engineering challenges.
All right, let's delve immediately into the most non-negotiable metric: latency. You frame 6G as scaling, but the leap from 5G's typical latency floor of around 1 millisecond, down to 6G's target of sub-1 microsecond, that's a 1,000-fold improvement. It cannot be achieved by scaling the current architecture. It's just not possible. 5G's latency is dominated not just by the error interface, but by transport network delays and core processing times. Even in a really optimized 5G standalone network, the packet has to traverse multiple hops to the user plane function in the central cloud, and that creates that insurmountable floor around 1 millisecond.
That's a compelling explanation of the physical constraint, I'll give you that. But I'd argue that the architectural solution, which is distributed compute, is an evolutionary response to that known constraint.
The edge computing movement, which decentralizes processing closer to the user, that began explicitly in 5G to address these very latency issues. You are right that 6G has to push this to an absolute extreme, but the concept of decentralized processing is inherited directly from 5G-A.
But the level of integration required for microsecond latency represents a revolutionary architectural break. 6G requires not just edge computing. It requires embedding AI inference engines co-located with the UPFs directly at every single radio access node. We're moving from a system where the UPF is centralized, even if it's at the edge, to a massively distributed, hyper-dense fabric where intelligence and user plane processing are fully integrated into the physical layer. This is what allows for predictive quality of service and eliminates those cloud round trips entirely. This radical distribution strategy, which is necessary to get past that millisecond floor, fundamentally breaks with the conceptual architecture of 5G, which still relied on a distinct, though localized, core network.
I'm sorry, but I just don't buy that it's a conceptual break. 5G introduced the concept of control and user plane separation, or CUPS, specifically to facilitate this very distribution of the UPF. 6G simply takes that separation to its logical, engineered extreme by embedding the UPF locally, but it utilizes the separation principle that 5G established. The reason this extreme distribution is necessary is purely to scale performance for THC communications in dense deployments, not because the foundational idea of decentralization is new. The performance gap forced an engineering change, a radical scaling, yes, but not a revolutionary conceptual rethink of the network function itself.
I see the continuity in the CUPS concept, sure, but the requirements for terahertz communication necessitate a paradigm shift in the air interface that 5G architecture simply cannot support. The throughput leap from, say, 20 gigabits per second in 5G to 1 terabit in 6G demands we unlock the THC spectrum. And this isn't just using a higher frequency. It introduces enormous new problems: extreme propagation loss, requiring pencil-thin beams, and atmospheric absorption. To make THC viable, we need exotic new materials for transceivers and entirely new methods of cooling and power management. When the solutions required involve changing the physical properties of the hardware and the fundamental physics used for transmission, that ceases to be an evolution. It's a technological discontinuity.
That's a compelling point. But have you considered that the industry proactively laid the foundation for that discontinuity within the evolutionary phase? The source material confirms that 5G-A began early terahertz band research specifically to tackle these issues. Why would you begin preparatory work inside the 5G envelope if the subsequent stage was going to be a clean architectural break? They anticipated the capacity wall and began the climb during the 5G phase. This gradual, intentional roadmap towards high-frequency exploitation confirms an evolutionary trajectory, even if the eventual implementation demands entirely new hardware.
Preparation is not implementation, and to achieve usable THZ communication indoors or in non-line-of-sight environments, we need a complete rethinking of network topology, and this brings me to cell-free massive MIMO and reconfigurable intelligent surfaces, or RIS. Cell-free massive MIMO entirely eliminates the traditional cell boundary concept, the very basis of every wireless generation since 2G. Instead of serving a user from one centralized tower, numerous distributed antenna points cooperate to serve the users simultaneously, delivering uniform quality of service across the entire area with no handovers. This is a revolutionary break from cellular topology.
I would frame that differently. While cell-free massive MIMO is a powerful innovation, its necessity arises directly from the scaling problems inherent in 5G massive MIMO deployment, particularly as we move toward higher frequency bands and denser user areas. 5G's massive MIMO improves spectral efficiency dramatically, but it exposed severe limitations at the cell edge, leading to the performance degradation you just mentioned. Cell-free MIMO is an engineering solution to mitigate those known scaling failures of the centralized cell concept. It builds directly on the mathematical framework of massive MIMO, but distributes the physical infrastructure to address high-frequency coverage gaps. It completes the vision of high-density, high-throughput coverage that 5G struggled to fulfill.
But RIS allows us to manipulate the very physics of the wireless channel. The source describes RIS as technology that allows us to program the wireless environment itself. These surfaces, they're made of metamaterials. They can dynamically reflect, refract, or absorb radio waves. This isn't just mitigating a problem, it's transforming passive surfaces like walls into active network components with near-zero power consumption. We're dynamically controlling propagation, solving 5G's crippling indoor penetration failures for millimeter wave frequencies. That capacity to actively shape the radio environment is a paradigm shift. It overturns decades of wireless engineering based on fixed, unpredictable channel characteristics.
Okay, that is a fascinating technical description of RIS, but look at its primary purpose in the 6G blueprint. It exists specifically to enable THZ and millimeter wave spectrum utilization in non-line-of-sight environments. It is the necessary component that makes the high-frequency scaling, which started in 5G, viable. The problem RIS solves is the propagation constraint that became acute when 5G scaled up to the M-wave bands. It facilitates evolution by overcoming a critical physical roadblock that threatened the 5G capacity vision. If 5G hadn't pushed us into that high-frequency, capacity-rich world, we would never have needed this revolutionary tool to fix the side effects. It's a tool for continuity, not discontinuity.
The most compelling evidence for revolution, however, is the fundamental shift in the network's mission. We are moving from a communication-centric network to an intelligent digital fabric that senses and predicts. The integration of ISAC means radio waves are doing dual duty. They simultaneously transmit data and sense the environment, tracking objects, measuring distance and velocity, recognizing gestures. The network is no longer just enabling connectivity, it is becoming the foundation for the digital twin of the planet, supporting entirely autonomous systems and merging the physical and digital worlds. The source material calls this a fundamental reimagining of wireless networks, and that change in purpose is a clear break from every previous generation which focused solely on connecting people and devices.
I agree that this sensing element is novel, but the necessity for the predictive and autonomous capabilities you are emphasizing is a direct evolutionary consequence of the complexity 5G introduced. Let's compare the intelligence. 5G introduced the NWDAF, the Network Data Analytics Function, which is fundamentally a reactive AI engine. It analyzes past data to optimize network slices or predict mobility.
And 6G?
6G introduces the AI native core, which is proactive and intent-based. But why? Because the virtualization, the massive scale of IoT, and the reliance on edge computing introduced by 5G created a perfect storm of operational complexity. Current 5G architectures managed by human operations or reactive systems like NWDAF struggle profoundly with autonomous orchestration, security, and slice management. The 6G AI native core is a necessary, forced response to the need for full autonomy, simply to manage the scale and complexity 5G created. The intelligence isn't a revolutionary goal in itself. It's a critical evolutionary requirement for operational stability.
But this sensing component ISAC is a pure paradigm shift. 5G's intelligence is focused inward, on optimizing network operations. 6G's intelligence is focused outward. How can you explain the ability of a radio wave to measure the distance and velocity of an object using beamforming as merely an evolution of 5G? The radio resource management layer is completely reframed when every piece of transmitted energy provides data not just to the receiver, but about the external physical environment.
That's an interesting point on the application of the radio layer, though I would frame it differently. ISAC is leveraging the advanced beamforming and massive MIMO techniques that were already perfected in 5G, techniques designed to pinpoint a user in three-dimensional space with extreme accuracy. By integrating advanced signal processing, 6G is simply extracting secondary environmental data from the existing high-resolution radio measurements, which were initially developed for communication purposes. It's an innovative expansion of the radio's utility, applying established 5G precision techniques to a novel purpose. The system is still fundamentally communicating, but now it has an integrated side effect. The necessity, however, still flows from the applications enabled by the capacity and low latency 5G promised, like autonomous vehicles, which require real-time sensing.
But those applications, holographic telepresence, digital twins, they require a performance matrix that is unattainable by 5G. The latency floor of 1 millisecond breaks the real-time interactivity loop needed for 3D mapping and rendering, making truly seamless immersion impossible. When the only way to achieve these transformative applications is to fundamentally rebuild the physical and logical layers using terahertz, distributed AI, and ISAC, you have triggered a revolution. It is technology designed to overcome the hard limits of its predecessor, not merely enhance its existing features.
This really highlights the core tension in our material. My argument remains that 6G is a necessary, aggressive evolutionary leap, succeeding where 5G's physical limits caused operational struggle. It relies deeply on the foundational preparation of 5G Advanced, whether that's through end-to-end standardization, the implementation of edge computing, or the initial research into high-frequency spectrum. And while the quantitative improvements are massive, the path is continuous, using powerful new technologies like RIS and self-free MIMO as sophisticated engineering solutions to scale up the core functional objectives, latency, coverage, and density, that 5G established. We are simply finishing the high-capacity virtualized vision that 5G initiated.
And all summarized by asserting that 6G is fundamentally revolutionary because its core architectural pillars, THZ, ISAC, RIS, and the AI native core were specifically introduced to intentionally bypass inherent physical and operational floors in 5G. These technologies enable a new generation of applications by transforming the network's purpose from connectivity provider into an intelligent, sensing environmental fabric. When you change the physics, the topology, and the core mission of the network, you have fundamentally redefined it. The thousand-fold leap in latency achieved by a fully distributed core is not evolution, it's a necessary architectural discontinuity.
Our discussion illustrates that the complex path of technological progression is rarely black and white. It relies on both the necessary incremental work and those moments of intense innovation. Whether this unprecedented leap is the culmination of an evolution or the undeniable start of a revolution, well, it really depends on where you draw the line between continuous improvement and an architectural break.
Indeed. It leaves the listener with plenty to contemplate as we watch this journey unfold toward 2030. And it certainly suggests there is much more rich technical detail to explore in the source material about how these competing forces truly define technological progression.